Okay. So we defined the SLE last time, and we have shown that if there is a conformally invariant curve which has some sort of Markov property, it has to be a SLE. Now there are basically two questions: how to study SLE curves, and how to show that indeed for some model the curve is a SLE. So the one option, of course, is you have some conformally invariant curve. So you have some curve, you show that it's conformally invariant and Markov property, then it has to be a SLE. Then you can figure out kappa from some by calculating anything. Now the question is how to show that it's conformally invariant. So it turns out that a much weaker statement is sufficient. So if you have a curve and you are able to calculate just one parameter of it and show that it's conformally invariant, then it has to be a SLE. It's more or less the same proof as calculating something for a SLE, only going backwards. So I will start with an example. So it's maybe the simplest example of calculation. So an example. So the method is due to Rode and Schramm. So suppose that we run, so we have a SLE and a SLE kappa curve. So it's the solution to the equation. So the equation was that the time derivative of the, so if I take map GT such that zero goes to, tip goes to the 0, and GT then has some expansion at infinity, z minus square root of kappa Brownian motion plus 2t over z plus so on. So that's the driving term is Brownian motion in this case. So its solution to the equation time derivative of GT is twice over GT minus square root of kappa Brownian motion. So it's some random curve. And let's fix a point z. And well, here, let's go look at the probability that this curve gamma passes right of the point z.
Isn't it bt prime?
Bt prime, yeah, bt dot. Yeah, if you do the usual stochastic calculus notation, then you would probably write just dgt is 2 over gt dt minus square root of kappa dbt. So if you want the eta calculus notation is that you do not derivative, you do differential. So the change in gt is change in time 2 over gt plus minus square root of kappa change in Brownian motion. Or maybe it's better, let me see, gamma passes right. Yes, yeah. So, so basically, well, maybe a few remarks. First, as time goes to infinity, eventually, well, the diameter of our curve goes to infinity. So eventually it will pass left or right of z. It might return and overpass it on the other side, but eventually the curve goes to infinity. So we haven't shown it yet, and maybe won't show it, but one can show that almost surely gamma of t goes to infinity. So it means that sooner or later it will leave like a ball of radius 1 million, and it will stay on the same side of zt. So it means that it's a well-defined so eventually it will reach infinity, and our point will be either to the left or to the right. Now, the event is well defined when kappa smaller than 8, because in this case area of our curve is equal to 0 almost surely. So it passes through the point with probability 0. When kappa is bigger than 8, we have a piano curve. We have not proved it yet. But in this case, left or right is not defined because we will just pass through this point almost surely. So for kappa bigger than 8, gamma will pass through just through the point Z almost surely. Okay, so how do we calculate this? So we observe so that there is this. Well, let us define a set. Look at this probability. Yeah, and maybe another thing is that another remark, a secondary remark, is that by conformal invariance we can just stretch or shrink our plane. So this probability for the point Z is equal to the probability for the point RZ because of conformal invariance if we send Z to RZ. So this probability depends only on argument of Z. So let's set new function f of theta to be that the probability that gamma is right of the point r e to the power I theta Now, what happens with this probability? For example, we have a simple curve. It completely determined at time infinity. When we hit infinity, we fix it, whether we're left or right. But as we grow, even if I draw it like that, I can, in principle, return and overtake on the other side. But as we draw, we can track the conditional probability that will be on the right, and we'll get more and more information. So for example, here it's already very much likely that Z is on the left. This conditional probability will be a martingale with respect to the Brownian motion, which drives our SLE, as we get more and more information. So we can formulate it that the probability of that gamma is right of some point, let's say, Z, conditioned on knowing gamma 0 T, is a martingale with respect to our Brownian motion. So this is just the sort of basic Martingale theorem that if it says that you have some event which is determined by our ultimate sigma algebra at infinity, when we run the time t and recover more and more information, then the conditional information is a martingale. So it's so for example, yeah, if our eventual probability is 1/2, and we start drawing our curve and we toss a coin and we go left, and in this case probability is 1/3, then when we go right it must be 2/3, so that averages to 1/2. Because the total, so it's just from the total probability formula. Now, this we can rewrite by conformal invariance. So look, the probability that we are right of this point, what we can do, we can open this up by the map GT. So there is this Z, there is this GT of Z point. So the probability that this curve passes left or right of Z is the same as the probability that its image passes, because SLE has domain Markov property and is conformally invariant. So this conditional probability can be just rewritten as that probability that GT, that gamma is right of GT of Z. So we just use the same property as a week ago, that SLE is conformally invariant, and that it has Markov property. If we run it for some time, when we open up this slit by conformal map, we again get SLE. And this function is just a function of argument of GT of Z, so it's argument of GT of Z. So this function is a Martingale. And you see, well, the important thing is that we dropped conditional probability, so we just have our function unknown, what is this probability depending on the argument. We plug in this random GT, and it turns out that this is a Martingale. And now we have, so I think I will on purpose do it in two ways. I will do it for some other quantity just with stochastic calculus and eta formula. And now I will just do it writing power series expansion for the Loewner map, just to see what does that mean. So let's do it. Well, it's more or less equivalent, but let's do it first without stochastic calculus. So we know that this is a Martingale. Now let me just put Z to be equal R e to the power I theta. So let's do some power series expansions. So what is GT of R e to the power I theta? Well, there is this expansion written here. So it's R to the power e I theta minus square root of kappa Brownian motion plus twice T over R e to the power I theta plus so on when R goes to infinity. Now, what I want to do the argument. So argument of this guy, GT power I theta, is equal to, so argument, well, I mean, it's the easiest just to write that it's an imaginary part of the logarithm of this number. And in principle, what I can do, well, the imaginary part of logarithm, the logarithm doesn't change when you divide by R, so I can just divide by R. So I will have this formula. So it's an expansion in R. And then I can write Taylor expansion for the logarithm. So maybe I'll do it on a different blackboard so that I have more space. So it will be, okay, so imaginary part of this. So it's the constant term is just, well, imaginary part of logarithm e I theta, plus then we'll have imaginary part of, well, we take derivative of logarithm, which is 1 over the number. So it will be, well, that's just theta. Plus derivative of logarithm is just 1 over the thing. And then we have to add the increment. So it's minus square root of kappa bt over R plus 2t over R squared e to the power I theta. Then we have to take second derivative. So if we logarithm is derivative 1 over x, second derivative is minus 1 over x squared. And we have to take 1/2 coefficient, so it's image of 1/2 of e to the power I twice theta. And you know what, maybe, yeah, twice minus square root of kappa bt over r plus twice t e to the power, what was that, like c over r squared e to the power I theta plus smaller order terms. And that has to be squared. And then the rest of expansion will be smaller terms than 1 over r and 1 over r squared. And you know, maybe I would just make a small remark. I started doing it for the Brownian motion, but let's maybe, for instance, say that we don't know, well, that what kind of process this is. So I would just denote this AT. So I just want to make some conclusion which holds not only for Brownian motion but for any Loewner evolution driven by any process. So we can just say that this is a driving force. So in our case it will be Brownian motion, but I will for a while pull it just as AT. So it's theta. Now the term with 1 over r will be what? It will be imaginary part. So with 1 over r the term is just this, e to the power theta, so it's e to the power minus I theta minus this AT over r. And now r squared I get squaring this, and then that is no longer important. And also from that term. And then from that term I get what? I get plus e to the power minus I theta twice t e to the power minus I theta again. And that's 1 over r squared. And from this I get minus 1/2 e to the power minus I twice theta. And I have a square of this term, so it will be a t squared plus some small order terms. So we have an expansion in R. And we now write imaginary part. So here it's cosine minus sine, and then there is minus in front. So it's plus sine theta AT over R. Here you have the same thing, exponential of minus I twice theta. So this thing will be minus sine twice theta, imaginary part. Well, here is minus sine, so it's plus, and I will get AT squared over 2, and this is with minus goes minus 4t. So 1 over r squared, plus no order terms. And now I expand my function f of argument of gt r e to the power I theta. So this is f of theta plus increment which we have here times f prime of theta times the square of this whole increment. So it's sine theta AT over r plus sine twice theta AT minus 4t over 2, 1 over r squared, and plus theta prime prime second derivative, square of the increment, again the meaningful term, only the first one, sine squared theta AT squared over r squared. And the final result is that it's f of theta plus the next term with 1 over r will be just this one. So it's how to put it better? f prime of theta sine theta 8c, plus the next term with 1 over r squared. Well, it has two parts. It has this part and it has this part. And sine, maybe it's better to collect them separately. So the first one is f prime of theta sine twice theta 8c squared minus 4c over 2. And the second one is f prime prime of theta sine squared of 2 theta over 2. 8c squared 1 over r squared plus more over the terms. Now, what have we achieved? Well, we had this thing. We had this thing for which we can write the expansion. We now written expansion for f, and for f we know that as we grow our how, this is a Martingale. Now we have a power series expansion. If it's Martingale, it just means that basically all the terms are Martingales in their own right. Because if I take r very, very large, these terms are much smaller than the first one, so the first one has to be a Martingale up to epsilon. Epsilon tends to 0, then it is a Martingale. Well, first one is a constant, so it is a Martingale. But now we subtract the constant, we see the next term. Again, it majorates the third one, so this has to be a Martingale. So individual, this term is a Martingale. And this one is also a Martingale. Now let's just do two things. So I will erase this thing. So what we conclude is that these two things matter. So for example, f prime of theta times the expectation of 8c is equal to 0. And for the second one, we do the same thing for expectation. We get f prime of theta, what was there? Sine twice theta, expectation of 8c squared minus 4c over 2. Well, maybe I put over 2 here, plus f prime prime theta, second derivative, sine square theta over 2, expectation of 8c squared is equal to 0. So what did I use so far? So I claimed we start for the Brownian motion, but in fact we use only one property. We use that you have some random curve and you can stretch it, stretch invariant. So we only used that this probability is scale invariant. Scale invariant RAS. And the second is that domain Markov. Conformally invariant and domain Markov. In particular, so there are two things. On one hand, if we have a curve where just this probability is domain Markov and conformally invariant, then we deduce this about the driving function. On the other hand, if we know the driving function, we can plug in the driving function into this equation and deduce something about this probability. So let's start maybe with the second one. So first, that assume that AT is square root of kappa BT. Then what is the expectation of AT squared? So it's the expectation of kappa Brownian motion squared at time t. Brownian motion time t squared expectation is t. So we get that it's exactly kappa t. So we plug in the second equation, let's say. This equation becomes f prime of theta sine twice theta over 2 kappa t minus 4t, kappa minus 4 times t, plus f prime prime of theta sine square theta over 2, kappa t is equal to 0. Immediately t we can cancel out, and that's sort of clear. We should get the same formula because of the rescaling for different values of t. Well, how do you usually solve these equations of this type? You move everything to one side. Well, you would move f prime to the other side, so you get f prime theta is equal to minus f prime theta sine twice theta over 2 kappa minus 4, and we have divided by this guy, so 2 over kappa sine squared theta. By the way, sine twice theta is twice sine theta cosine theta, so one of the signs goes away. Number 2 and number 2 go away. So we get what? We get number 2, kappa minus 4 over kappa, that will be just 1 minus 4 over kappa. And we get cosine over sine, it's cotangent of theta. Yes. But there was a minus sign in front. Wait a second. Yeah, so it's minus this times f prime theta. So if we divide, we get that the logarithmic derivative of f prime of theta. So if we do this derivative is f prime over f prime. So we get that this ratio is equal whatever we have written there. So let me just put it 2, 4 over kappa minus 1, cotangent of theta. So that means that logarithm of f prime theta is what? Is constant plus integral of twice 4 over kappa minus 1 cotangent theta. Any chance someone remembers what is the integral of cotangent theta? Well, okay, nowadays I can always look up in some big book. What's the integral of cotangent? Yeah, I think it's logarithm over sine, or yeah, logarithm over sine. So it's constant plus this number times logarithm over sine. So logarithms here we can exponentiate. So when we get as a result that f prime of theta is constant times sine theta to some fractional power. Or if we integrate, it's constant times integral of this guy plus another constant. And what we know about the boundary conditions. So when we're here, theta equals 0, then f is equal to 0, because you are always to the right of the curve. If you are on this boundary, the curve is left of you. Then when theta is equal to pi, f is equal to 1, because if you are here, then the curve is always right of you. So the constants you can figure out because of that. So the constants will be, this will be 0, because at 0 you should get 0. And the constant at pi should be just this integral from 0 to pi. So f of theta is integral from 0 to theta sine theta 2 over 4 kappa minus 1, divided by the same integral from 0 to pi. So this is the exact formula that SLE passes to the left of some point. So what I did here, it's essentially the same thing which you would do if you do eta calculus, but we pretended we don't know eta calculus. So we did expansion in a big values of r. In eta calculus, it would correspond to expansion in small values of time epsilon. But the formulas will be exactly the same. If you are familiar with eta calculus, it is slightly shorter to do it there. Here, on the other hand, you a priori don't need to know any eta calculus, and what I did, it works for any process, even if you don't have, you don't know how to differentiate that particular process. Now, this is the exact formula. The proof is rigorous as far as our thing is well defined. So the remark is that it's sort of complete proof we did. Modulo 2 thinks that area of gamma t is 0, so and gamma t goes to infinity, so gamma t almost surely is either right or left of our point eventually. So we only assume this. We have not shown that this is true for SLE yet, but it is. Now, what happens if kappa is bigger than 8? So if kappa is bigger than 8, you don't have these properties. But also this integral will break down. Because if kappa is bigger than 8, then 4 over kappa is smaller than 1/2. 1/2 minus 1 gives you minus 1/2, times 2 it gives you minus 1. So you won't be able to integrate it near 0. It will be non-integrable singularity. So it's for kappa bigger than 8, integral diverges, which is quite fine because object doesn't make sense. Usually you cannot calculate this integral, so this is one of the hypergeometric functions. So there is a special notation that's basically simplest function you cannot integrate. So if you start trying to integrate like you are taught in school or university, then of course one thing one tries is to do substitution, sine for cosine change to another variable x, and then in this case you will get sine, but also cosine will pop out. So you have some powers of x and some powers of 1 minus x squared. So you'll be integrated fractional power of some polynomial with two singularities. And in general, it's not integrable, so there are some specific cases when it is. So for example, kappa equal 4, kappa equal 4, the power is 0, so integrate a constant. So you just get theta. For kappa equal 4, you get that f of theta is theta over pi. So it's just, maybe let me just do it as an exercise. You look at this function and establish the form. So kappa equal 4 is easy, and kappa equal 8/3 is easy, and kappa equal 2 is easy. You get nice formulas because you get nice power, so it's theta of is 1 minus cosine theta over pi, and here it's theta over pi minus sine twice theta over 2 pi. So this is a very nice formula, and this is a very nice value of kappa. It's the value of kappa which gives you conjecturally self-avoiding polymers. But we don't know how to use that this formula is nice. This formula being nice, it's actually easier to use because the function here, the argument, so this function is harmonic. So the function argument of z is harmonic in the plane because it's the same as imaginary part of logarithm. Logarithm is an analytic function. So its imaginary part is harmonic. So this is harmonic. So basically, what happens if you run SLE4 from here to here, and you ask what is the probability that you pass to the right or left of point? You take boundary value 0 here, boundary values 1 here, because the curve is always to the right of these points and to the left of this, and then you take harmonic function in between with these boundary values. The solution of the Dirichlet problem. It tells you probability that you passed to the left of a point. So for SLE4, SLE4 is in a sense much nicer curve. It's much more straightforwardly connected to harmonic and analytic functions than the other ones. And the other ones, honestly speaking, we don't understand. So there should be a similar connection for the other SLEs, but with some complex twist. And honestly speaking, people, me included, don't understand it very well. Okay, now that's the proof in one direction. Now let's go the other way around. So the second part. So suppose for some curve gamma, this probability is conformally invariant, well, domain Markov, and given by the formula. By this formula, let's say, the snowflake formula. Then what do we get? We can take our original equations. So the equations what will they read? The first one is f prime theta expectation of it is equal to 0. Since f is basically very much a non-trivial function, we can plug in some theta where the derivative is non-zero. So we conclude that expectation of at is equal to 0. Now, also for this function theta, we have, so what does theta, well, this function, yeah, okay, so that's the first equation. Now the second equation was f prime prime theta sine twice theta over 2 exponential of at squared minus 4t plus f prime of theta, was it plus sine squared over theta over 2 exponential of at squared is equal to 0. So that's the equation star. But our function, it also solves this equation. So our function is a solution of this equation. But f of theta also solves equation f prime theta sine twice theta over 2 kappa t minus 4t plus f prime theta sine twice theta over 2 kappa t is equal to 0. So if we have these two identities and theta pretty much, well, takes different values, it means that ratio of these two things is the same as the ratio of that two things. Just the linear algebra, because we plug in values of f of theta, non-trivial function in different points, but still the equation remains, so it means that the ratio of these coefficients and the ratio of these coefficients are the same. So we conclude that, well, how to put it, what's the best way? Expectation of at squared minus 4t over kappa minus 4 times t is equal to expectation of at squared over kappa t. Well, t we again take out. So we conclude that expectation of at squared minus 4t is equal to expectation of at squared, and that we move here kappa minus 4 over kappa, which actually happens to be 1 minus 4 over kappa. Wait a second. No, that is plainly, what is it? I should get slightly different thing. I should get what? I should get that expectation of at is, no, I think I'm fine, yes. Okay, so when we move it to the other side, we get expectation of at squared. We had 1 on the left, we have this on the right, minus kappa minus 4 over kappa is equal to 4t. Now, this guy is 4 over kappa, so we just multiply by kappa over 4. So what we get is that expectation of at squared is equal to kappa t. So we deduce two things. We deduce that expectation of at is equal to 0, and expectation of at squared minus 4t, minus kappa t is equal to 0. So this is obviously true for Brownian motion. Does it characterize the Brownian motion? Well, not yet, because we only have it for values of t. You need some more properties, like, for example, if you know that your process has independent increments and is Markov, that is enough. But there is a much stronger theorem that apparently, if you know this for increments, and we can do it for increments, because what I did, I ran it from 0 to t, and I looked at Martingale property from 0 to t. But you can run it from t to t plus s and look for Martingale property there. So the remark is that you have the same property. So for this we ran from 0 to t. But if we run from let's say s to t plus s, we get same for increments. So basically, you would have something like expectation of s plus t given process up to time s, let's say given gamma 0s is equal to as, and we'll have the same thing here. And that apparently, if you have the same for increments, there is a theorem of Levy, of Paul Levy. So theorem, well, just it's common enough, so people say Levy theorem, that to conclude that at is square root of kappa Brownian motion. So let's say for an increment, so maybe I've just formulated as that in the following way, that HC Martingale and HC squared minus kappa T Martingale. Amanda, did you have Levy theorem? No? Yes. Ah, okay, great. It's again, I mean, the theorem, it's nice to recall it because it's the universal property of Brownian motion. Basically tells that if you have a nice process, it's enough to know increments and squared increments, that it uniquely characterizes Brownian motion if they are appropriate. Okay. So the second part was that, so basically we've shown that if there is an SLE kappa, we can calculate what is the probability to pass of the left point. Then on the other hand, if you have some other process for which you can calculate the probability to pass to the left of a point, and it turns out to be the same for SLE as for SLE kappa, it has to be SLE kappa. So to show that, for example, suppose you want to show that random polymer model converges to SLE 8/3. You don't need to prove that it has a conformally invariant limit. You just need to prove that probability that a random polymer pass to the left of point is given by conformally invariant formula of 1 minus cosine theta over pi. So we map to. So just calculating one thing is enough to show this. Now you can, yeah, maybe I'll finish, so I'll chew off 5 minutes from the second half. So you might ask, and what if you calculate the probability to pass to the left? It's given by some formula, but it's not this formula. What will happen? Well, the following thing will happen. You will plug it in here. You will get these ratios. And then it will completely break because you will get a conclusion, something like that, well, which will be self-contradictory. Because for different values of theta, you will have different ratios. And then if you don't have this exact identity, and you'll get a self-contradictory conclusion that expectation of AT squared, if you prove it with one value of theta, has one value. With another value of theta, it has another value. So it's kind of a method which is self-checking in the sense that if you prove and you don't get this function, it means that you screwed up somewhere because you get a contradiction in mathematics. So maybe to specify a little bit, just elaborate on this, I'll just return where we had this AT. Yeah, so it's, yeah, okay, I'll return to this. So let's say 3. So suppose there is some curve, some gamma, which is where f of theta is conformally invariant and domain Markov. Then when we write all of our equations, so this equation star the other one will mean that expectation of AT is equal to 0, we already have written. But also it will mean that expectation of AT squared minus 4t, so what was that? This times, where did I have it? Yeah, times f prime theta sine theta over 2. No, that was f prime prime theta sine twice theta over 2 plus expectation of AT squared f prime theta sine. So one of them was square and one of them was just sine. Yeah, this sine twice theta over 2, so that was sine square theta. Expectation of AT squared is equal to 0. So it will imply that the ratio, the expectation of AT squared minus 4t over the expectation of AT squared will be equal to minus f prime prime theta over f prime theta times tangent of theta over 2. And what is interesting about this equation is that the right-hand side depends on theta and left-hand side depends on t. So you have two functions which are equal of two different variables. One depends on t, one depends on theta. Which means that they are always constant. Because if one of them is non-constant, you get a contradiction. You change t without changing theta. So it's function one of it's a function of theta. This one is function of t. So what you get is that expectation of at squared minus 4t is some constant expectation of at squared, which means that expectation of at squared is equal, so if you know this constant, it will be equal to 4 over, you move it, 1 minus c times t. So it just plays role of kappa. But also you get that f prime prime theta over f prime theta is equal to twice cotangent theta times this constant. And again, you can solve the equation. So essentially, it's very rigid. Only SLE kappa are the curves for which you can have, even for a single observable, this property that it's conformally invariant. So if you calculate for some curve something, it doesn't matter, probability of passing to the left, probability of whatever, of touching the epsilon neighborhood, that you have to be careful to make conformally invariant. Well, one can, you multiply by f prime at this point or something. So whatever you calculate, it's enough to show that the curve is a SLE. There are no other curves which have this nice property, which is of course a good news. And let's have a break. Okay, now we will try to calculate something a bit more difficult. Now the problem, of course, with this calculation is that whatever you can come up with, you can write an equation for. So for example, if you have thing which is conformally invariant function of 5 points, you can write equation, but it will have, for 1 point you have real and imaginary coordinate, for 5 points you will have 10 coordinates, so it will be equation of 10 variables, and it's not clear you will be able to solve it. So of course, if you know the solution because of some physics intuition or something else, then you can show off the solution, and then you get to prove that this is a solution. But if you don't know it, then it might be difficult. And for example, if I just ask the following question, so I'll write you, say, 5 points, and what is the probability that the SLE passes to the left of the first 3 and to the right of the last 3? So there is, as far as actually I don't, off the top of my head, remember, but here I think there is no easy answer because the physics quantities of importance, they count slightly in a different way. So, okay, so so I want to do one simple calculation today, one more simple calculation, and no complicated ones. So we'll try to, so as I said, that there are SLE phases that for kappa smaller than 4 almost surely simple. For kappa between 8 and 4, for including, it's almost surely self-touching. So it's a curve which goes something like that. Now self-touching, I mean that what happens here is that there is a counter set where it touches itself. So so during any time epsilon interval, it will touch itself infinitely often. But it leaves these gaps, and by the way, each gap is either on the right or on the left. So if you just fatten the curve a little bit, you will see it. So for example, here these gaps are on the left and these gaps are on the right. And for kappa bigger than 8, you have almost surely Peano curve, which is space filling. So the same, but it doesn't leave the gaps. So how do we will like almost prove it almost in two ways? So let's first start with the first one. So let's say kappa is smaller than 4. And what I want to do, let's so suppose that so let's show that almost surely simple. So it's the same as almost surely does not touch itself. And it's the same as it does not touch the real line. So, because what does it mean that it touches itself at one point? It means by conformal invariance, if I, so for example, it touched itself at time t and this is time s, so what I can do, I can open up it up to time s, and then this picture will become a picture like that, that it touched the real line. So if it touches itself, then it means it touches real life, and the other way around, just because of this opening. So doesn't touch real line, it's much easier. So it's what does it mean that it touches the real line? So suppose that it touches the real line here. What happens to all these points in that moment? From the point of viewer at the infinity, he sees that the tip and these points are very close. And the moment of touch, they collapse to the tip, so they will collapse to 0. So does not touch R, it means that for, it's the same as saying that x, gt of x, where x is in R, almost surely doesn't tend to 0. So if it stays away, then it's always visible, then everything is fine. So that we will prove. It's kind of technologically very bad with this when they changed this blackboard 5 years ago, because water is dripping into it and people put chalk. Yeah, so it's a nightmare. Okay, so let's denote this by xt. So what is the what we will do? Let's first take some interval a and some interval b from a to b. So let's say 0 smaller than a, smaller than b, smaller than infinity. And let's take like x 0 in this interval. Well, maybe inside. And xt is just the gt of x0. So the equation for xt is 2 over xt dt minus square root kappa dt. So now we'll do it with eta calculus, though again one can do with expansion. So the simplification in this equation is enormous because we have a real number, not a complex. When we had a complex number inside the plane, then this was two real equations and complicated ones. Now it's much easier, it's just a real number. So it's one real equation. Okay, now so xt will move around by this diffusion, and almost surely xt will at some time tau, random time tau, leave the interval ab. Why? Because Brownian motion almost surely leaves the interval. And here we have drifted one direction, so it makes living in this direction more likely. So we have Brownian motion with definite speed, I have drift which is bounded away from 0 and infinity on the interval. So let's say that the new function, well, whatever was, well, let's say v of x, is that probability we live through point B. So v of B is equal to 1, v of A is equal to 0. So it's probability that we live through point B. So if it were just a Brownian motion, then it would be harmonic function. So it will be linear between 0 and 1. But here it's non-linear. So v of xt is a Martingale. So it's the same thing that at time, now not infinite time, at time tau when we hit, we learn whether we left through right or through left. But as we travel, we gain more and more information about it. We gain more information about trajectory. We are closer to B, it's more likely that we'll hit there. Closer to A, we'll hit more likely than we'll hit there. So it's just the same trick. So the reason why it's a Martingale, it's just that by conformal invariance. So v of xt is v of gt of x0. So the same thing, gt of x0. Now let's calculate its drift, dv of xt. So we get the usual equation. So it's v prime. Now this drift of xt plus v prime prime over 2. Well, basically drift of xt squared. So the term with Brownian motion only comes up. So we get v prime times 2 over xt dt minus square root of kappa dbt plus v prime prime over 2. And then dB squared is dt, so we get kappa dt. So it basically is dt times twice over x v prime of x plus kappa over 2 v prime prime of x plus well, minus something dB. Since it's a Martingale, there is no drift. So we have a process which is Brownian motion plus a drift. It's a Martingale, so there is no drift. So it implies that 2 over x v prime plus kappa over 2 v prime prime is equal to 0. So v prime prime over v prime, which is logarithmic derivative just like before, is equal to minus 4 over kappa x. So logarithm of v prime is a constant plus integral of this, and integral of this is minus 4 over kappa log x. So v prime we exponentiate is a constant, well, another constant times x to the power minus 4 over kappa, and v is constant plus another constant integral of that, x to the power 1 minus 4 over kappa. So this is when kappa is not equal to 4, and when kappa is equal to 4, it will be logarithm. And then we can remember the boundary conditions. So it should change from 0 to 1, from A to B. So we get that v is equal to v of x is equal to, let's say, f of x minus f of a over f of b minus f of a, where f is equal to either x to the power 1 minus 4 over kappa or logarithm of x. So what happens with these functions? So when you immediately notice that when kappa smaller than something happens funny at kappa equal 4. So that's the reason why theorem is. So when kappa is smaller than 4, so what happens? When kappa is smaller than 4, basically, so kappa smaller than 4, we get a function which looks, kappa smaller than 4, it's negative power. So it, wait a second, should I? Yeah, it's when kappa smaller than 4, you should get negative power. So what logarithm? Yeah, okay. Yeah, so if kappa smaller than 4, suppose that what happens when a tends to 0? So we take our line and we take interval where a goes to 0. Then we get x to the power 1 minus 4 over kappa minus epsilon to the power 1 minus 4 over kappa b to the power 1 minus 4 over kappa minus epsilon to the power 1 minus 4 over kappa. Now epsilon to the negative power is a very large number. So 1 minus 4 over kappa is negative. And this is a very large number. So basically we get something which tends to 1. Well, maybe it's better to write it like that so that you get two positive numbers. So if a goes to 0, then v goes to 1. So if you take this interval and you move left boundary, then probability that you exit through the right tends to 1. You see, it's not true if you just do it for Brownian motion. If you start Brownian motion roughly in the middle between 0 and b, it's half-half, you go left or you go right. But here there is a strong drift to the right, and when kappa is smaller than 4, it's strong enough that you drift to the right, you don't hit 0. Because the closer you're to 0, then the stronger is this drift. The closer to 0, then 2 over x, the stronger is the drift, so it's stronger and stronger pushes you. And when kappa is smaller than 4, this drift can overcome this square root of kappa Brownian motion. But when kappa is bigger than 4, the Brownian motion overtakes. So that's basically the thing. So what happens is that for kappa smaller than 4, kappa smaller than 4, small equal than 4, almost surely v of x ab tends to 1 as a tends to 0. So almost surely xt escapes to infinity. So when you draw this curve, you don't touch, but when you open it up, what happens is that this point xt is almost surely surpasses any b, so it escapes to infinity, the curve doesn't go through it. So the curve is simple. So this is just, for the process, it just means that when kappa is more than 4, this thing overcomes it. Now this is completely rigorous proof. Now I will just say the idea what happens between 4 and 8. When kappa is bigger than 4, almost surely v of ab x tends to 0 as a tends to 0. So the longer is this interval, the more likely that you will, so if the interval, this interval is long, you don't exit on the right. So what you can get, from this, you can get actually that almost surely, eventually, eventually xt is equal to 0. So eventually you pass through this point. Or you collapse it, so almost surely eventually xt goes to 0, so you touch on the right of this point. So basically to do it rigorously, the idea is that the following, that you take points A equal to 1, 1/2, 1/4, and so on. And you see that with positive, you hit 1/2, then you hit 1/4, then you hit 1/8, and so on. And you can estimate actually that you get it always with the, if you push the boundary on the right to the right, you get it always with probability 1. And the only tricky thing is estimate that you reach 0 in finite time. So we should estimate that the 0 is reached in finite time. So you should estimate how much time it gives you to get from 1 to 1/2, 1/2 to 1/4, but turns out that it's a geometric progression. So if you can get from 1 to 1/2 in some number of seconds, then we have conformal invariance, we can rescale, and the time will be rescaled. It will take smaller time to get from 1/2 to 1/4 because it's a shorter distance when rescaling. So the time tau 1 from 1 to 1/2, tau 2 from 1/2 to 1/4. So there will be geometric progression, so they will sum up. But of course, normally, if one wants to do all the rigorous things, one has to estimate something like expectations or expectations squared. So I don't want to do it, but I would rather outline a different approach. So it's a slightly different approach. Did you mention Bessel processes?
It was in the exercise sheet.
Yes, yeah, okay, so that's what I thought. Some small reminder. So what we're actually working with is called Bessel process. So this is d-dimensional Bessel process is the absolute value of the Brownian motion in Rd. So what is the Brownian motion in Rd? Well, Brownian motion in Rd is the independent collection of d Brownian motions. And the absolute value is just the square root of sum of bjt squared, j from 1 to d. Now this Bessel process, what was the letter for Bessel process, Dima? What was the letter? I don't remember. U? Well, whatever.
I think I used W first.
W, yeah, okay. So let's say WD, where B stands for Brown and W stands for Wiener, yeah. So the drift for the Bessel process, so it's possible to calculate, you just do the stochastic calculus with several Brownian motions, is, now I always, so what is it? So D is d minus 1, 4 over d minus 1. Well, let's say alpha over Wt minus dt minus dwt, where alpha is equal, if I recall correctly, 4 over d minus 1. Or is it d minus 1 over 4? So alpha should be equal to 0 if we have one-dimensional Brownian motion. Now I probably screwed it up. D minus 1 over 2, yeah. D minus 1 over 2. I think it's that, yeah. Now, with this definition, you don't have to take alpha d, which is integer. You can take any value of d. So it makes sense. So Brownian motion in space dimension 7 over 2 doesn't make sense, but its absolute value does make sense by this formula. So Brownian motion is recurrent for dimension smaller than 2 and non-recurrent for the dimension bigger than 2. Now for dimension equal to, it's sort of more subtle behavior. So basically for this coefficient it means that for alpha d equal to 2, alpha is equal to 1/2, alpha smaller than 1/2, alpha bigger than 1/2. So basically Bessel process, it hits 0 if alpha is small, and it doesn't hit 0 if alpha is large. So when alpha is large, this drift repels it strong enough that you don't hit 0, and for an alpha is small, it doesn't. Now, what does it have to do with our thing? Well, basically, we just draw the same thing. Let me just write it once again. So let's say that let's have a look at our equation. So we have equation that dxt. So we write it up to time tau when xt hits 0. dxt is equal to 2 over xt minus square root of kappa d Brownian motion. Now I want to use the same normalization. I want to, wait a second, now it will turn out that I screwed it up a little bit. Yeah. Yeah, it should be dBt. Yeah, dBt. Sorry. Yeah, dBt. No, I'm just trying to calculate. No, I don't think I screwed it up. So we want to get coefficient 1 here, so we divide by square root of kappa. So we get dxt over square root of kappa is equal. Now we had here xt. We should also first we divide it by square root of kappa. But we also need to write xt over square root of kappa. So to cancel it out, we need another kappa. So it's so this kappa, half of it came from me dividing by square root of kappa, and the other half for putting square root of kappa here minus dBt. So basically that's the Bessel process. This is Wt, this is Wt. And d minus 1 over 2 is equal to 2 over kappa. So that you can rewrite the dimension is 1 plus 4 over kappa. Or you can rewrite that kappa is 4 over dimension minus 1. Now, this is already, Bessel processes are such subjects that about them lots of books are written. So if you, well, I mean, first, what we need is easy to calculate, but also if you need something more complicated, you just go to the library and pick up one of those books. So it's easy to find them. Now, what happens is that when kappa is smaller or equal than 4, we get that d is at least 2, and we get that xt almost surely does not hit 0. So the gamma is simple, almost surely. On the other hand, when kappa is bigger than 4, d smaller than 2, xt almost surely hits 0 at finite time. So our point is slowed. Now, what is the difference between smaller than 8 and bigger than 8? So I don't want to do, I don't want to do it literally. I will just write one property so that for kappa smaller than 8, bigger than 4, probability that time when x1 is slowed is equal to time that the x2 is slowed is positive. And for kappa bigger than 8 or equal, then time when x1 is slowed is always smaller than time when x2 is slowed. So here, between 4 and 8, if you have 2 points next to each other, there is a positive chance that they will be swallowed at the same time. And you create this lake, and they are both on the boundary of this lake. What happens per kappa bigger than 8 is that you grow this piano curve. So you grow, and you swallows one by one. It doesn't surround areas. It just swallows points one by one continuously. So that in principle is just the property of the Bessel processes, that when drift becomes large, then it eats points sort of one at a time, and in some interval it just can collapse the intervals. Now I will do a slightly different calculation of that. So I don't. So this in principle. So if you, for example, a graduate student in probability, normally you know these properties of the Bessel processes, but we will just calculate something similar. So we will calculate a probability. Well, we'll calculate exactly that probability. So let's assume that we calculate the probability that, let's say, tau of x is equal to tau of u. So this is the probability that you have point x, you have point u. So it's the probability that they are swallowed at the same time. And also, if you deal with some lattice model, so remember that when we had lattice models, when we mentioned Ising model or percolation, that our curve, our interface was going so that you have a yellow cluster on one side and blue cluster on the other side. So if you have this picture, there is a yellow cluster which goes like that. So it means that there is a yellow arc which reaches from this arc interval to that interval. So it's the probability that there is a yellow arc which connects these two. So if your curve, discrete curve, comes from a percolation model or Ising model, which traces yellow clusters on the right, this is the probability that there is a yellow cluster which connects these two intervals. Or, equivalently, this is 1 minus probability that there is an opposite color cluster which connects two other intervals. Because the other probability would be that your curve hits here, and then what you have a blue cluster on the left, which goes like that and connects these two intervals. Of course, it doesn't make sense yet for the SLE, it makes sense for the lattice model. So for example, you study Ising model, or you study percolation, you reduce it to SLE. If you want for percolation to calculate the probability of having a connection, then in the limit it will be given just by this probability, which we are about to calculate. Now, how do we calculate it? So this is a biconformal invariance. This is a function of x, where x is, let's say, I want some ratio of x and u. Let's take ratio of x over u minus x. You can take any ratio, x over u, u over x, but with some ratios the calculations are easier. Here they are easy because in the denominator I will take the difference of two SLEs and the Brownian motion will cancel out. So what do I know about boundary conditions? Phi of 0. So phi of 0 is when x is equal to 0, so it's this picture. So for percolation it's clear that you won't have a crossing from one point to an interval because there is no ways to land. And for SLE it's clear that this point will be swallowed in epsilon time, whereas this will be swallowed later. So f of 0 is 0. On the contrary, phi of 1, so what, not of 1, of infinity. So phi of infinity is when u is close to x, so it's this point. Then, of course, most likely they will be swallowed at the same time because they are very close. So those are the boundary conditions. And now we have 5 minutes to write the martingales. So this is a martingale. Now, what is the drift of x? drift of x is 2 over x dt minus square root of kappa dbt. Now, what is the drift of u minus x? So the drift of u minus x, I subtract the same formula for x and for u, and oh miracle, the second term cancels out. So it's 2 over x minus, 2 over u minus 2 over x dt minus square root of kappa minus square root of kappa bt. So this term cancels out. That's why I wrote ratio x to u minus x rather than x to over u, because otherwise the equation would be slightly more complicated. Now, what is the differential of 1 over u minus x? Well, its derivative of function 1 over something is 1 over something squared with minus sign. So it's the derivative of this function times du minus x plus second derivative is 1/2 of the second derivative. The second derivative is now third power. And then I need to take the square of this term, but this term doesn't exist. So du minus x squared doesn't exist because there is no Brownian motion. So that's the simplification. Wait a second, what did I, du minus x, yeah. So it's just minus 1 over u minus x squared. Du minus x is twice 2 over u minus 2 over x dt. Yeah, maybe I simplify it. So I simplify it to be 2 over u minus x squared, and this will give me u minus x, so 1 will cancel out, or rather x minus u and minus will cancel out, so it's u minus x times ux dt. Now, I want to do the drift of x over u minus x, and it will be x times the drift of 1 over u minus x plus drift of x times 1 over u minus x, and there will be no term when you pull from both drifts because there is no Brownian motion in the second one. So there is plus. In principle, you have also this term usually, but there is no this term because there is no Brownian motion in the second guy. So that will be 2 over x, 1 over u minus x from here. From here it will be plus 2 times x times ux u minus x dt. And with the Brownian motion it will be minus square root of kappa u minus x from here dbt. Okay, and the remaining thing that I write drift of my function d phi of x. So it's phi prime drift of x over u minus x plus phi prime prime over 2. This drift squared, so the Brownian term. So what I get, I will just write term in front of dt. So the phi prime will give me this term. So it's 2 over x u minus x plus twice x ux u minus x. And the second one will give you phi prime prime over 2. And then you need to square this coefficient, so it's kappa over u minus x squared. So this is dt plus dbt something. So Martingale means that this thing is 0, because it's a Martingale. So once again, I get an equation for phi prime, but phi prime is a function phi is a function of x small. X small is x over u minus x. So I need to rewrite this in terms of x small. If I don't get it in terms of x small, it means that I screwed up something and made a mistake, because it should be possible to write it in terms of x small. What we do, so this is equal to 0, u minus x squared, I can multiply immediately by it, so I get an equation that is, let's say, phi prime prime is equal to minus phi prime, and then there is this big thing, 2 over x u minus x plus 2x over ux u minus x divided by this guy, kappa over 2 u minus x squared. So I need to simplify. Well, 2 I can plug out, kappa I can plug out, this 2 also, so it's 4 over kappa. Now u minus x squared I can move inside here, so I get 2 so I'll get 2 over x plus 2, well, this x cancelled out, 2 over u multiplied by u minus x. Wait a second, no, 2 I already took away. So this has to be calculated. So what I have? I have 1 over x plus 1 over u times u minus x. So this will be, if I plug this in, it will be u over x minus 1 plus 1 minus x over u. So it's u over x minus x over u. And now my term, so what was the term u small? It was x over u minus x. So 1 over u small is u over x minus 1. So u over x is 1 plus 1 over u. And x over u is 1 over 1 plus 1 over u. So it's u over u plus 1. So you get minus u over u plus 1. And that, in turn, if we cancel it out, it will be 1 over u minus 1 over u plus 1. Now I get, wait a second, let me check, because I get the number plus here. No, plus, yeah, plus, yeah. So I'm returning to my equation. Phi prime prime over phi prime is equal to minus 4 over kappa times 1 over u plus 1 over u plus 1. So you see, again, we again get logarithmic derivative of our observable, which allows us to solve the equation. So I do the same thing, that it's logarithm phi prime. Let me just write the result. So we get that phi is equal to c1 plus c2 integral from 0 to u 0 to u of u times 1 plus u over minus 4 over kappa du. And the constants you can figure out by the boundary conditions. So the first constant is 0, and the second you should normalize by the integral. So it's actually phi is equal to integral from 0 to u of this guy divided by the same integral from 0 to infinity. So that's the formula. So it makes sense for kappa bigger than 4. Because for kappa bigger than 4, singularity at 0 will be integrable, otherwise it's not. So that is for u at 0. But also we need this integrable to be converge at infinity. And converge at infinity with some two singularities. So you need kappa smaller than 8. Oops. So this makes sense between 4 and 8. Because at 0 we need 1 over u to the power 4 over kappa, and at infinity we need 1 over u to the power 8 over kappa, which is the sum of two singularities. So this is the probability that we throw 2 points at the same time, and it's also probability of a crossing. And at first this formula appeared when John Cardy calculated the crossing probabilities for percolation. He got exactly this formula for kappa equals 6. So power 2/3, it's a hypergeometric function. Now, and then it can be related to a SLE. So here it's the same thing. So for example, if you use the first half of this lecture, suppose that someone for percolation or Ising model calculates the probability of a cluster connecting two arcs and shows that it's equal to this formula in the limit. Then immediately you deduce that interface is a SLE with the corresponding value of kappa. Okay. So it all looks bright, but once you get more than 1 point, you get equations which are too difficult to solve, because here we have ordinary differential equation in x. If you have 2 points, you have system in x and y, and that might become too complicated. Not always, but sometimes it does. So next time we'll show that something converges to percolation, so it's either percolation, some converges to SLE, either percolation or Ising or uniform spanning tree, whatever. Okay, thanks.